So that brings us to Einstein. Einstein was always fascinated by light for most of his life. From the time he was a child, he was fascinated by light. And Einstein was also very interested, as a result of this, in Maxwell's equations. And he became familiar with the Michelson-Morley experiment and this weird, bizarre result that they got. So Einstein, rather than just dismissing these things as artifacts, as irrelevant things, he said, well, what if that's actually true? Because there seems to be a theoretical basis. It shows up in the math, which works well for everything else. And we have this experimental result, which both show the same thing, that the speed of light is the same for all observers. What if that is true? What would that do to physics? So Einstein came up with some postulates. Now, a postulate is an assumption that you make, that you accept to be true, and then you draw your conclusions from those things which you assume to be true. That's what a postulate is. You've probably seen that word before in geometry, because when you did proofs in geometry, there were certain postulates things you assume to be true, and then you move forward from there. So you need to know Einstein's postulates, okay? So make sure you write these down. Einstein's first postulate, is that the laws of physics are the same of everyone as long as they are not accelerating. So what this means is that if you are not moving with respect to your surroundings, or you're moving at constant velocity, something like that, that the laws of physics will be the same for you as they are for anyone else who's moving at constant velocity. So if you're the guy standing in the back of the pickup truck and you have the baseball and you throw the ball, well, you're applying a certain force to a certain mass of the baseball, and the baseball will accelerate according to F equals ma. And that's what you will observe if you're just standing in the back of the truck. Now, if the truck is driving down the street, the baseball will behave the same way as long as you are not accelerating. If you're just going at 60 miles an hour down the street, and you're standing, let's call it inside a bus, so that the wind is making a difference, and you throw the baseball will behave the same as it does when the car is not moving, for you, from your point of view. If you drop the baseball, it will go straight down. It will land at your feet if the car is parked and just not moving. And likewise, if the truck is moving down the road at 60 miles per hour at constant velocity, constant speed, not turning, just going straight, constant velocity, if you drop the ball, it will fall straight down and land at your feet. The laws of physics are the same for everyone, regardless of what they're doing, as long as they're moving at constant velocity. Okay. And Isaac Newton would agree with this one. He would say, yeah, that's absolutely true, because all motion is relative, and yeah, laws of physics are what they are. Okay, that's the first postulate. Laws of physics are the same for everyone. Now, second postulate is that the speed of light is the same for all observers, regardless of the motion of the light source or the motion of the observer. So no matter how fast you're moving, no matter what you're doing, no matter how fast the light source is moving, you will always record the speed of light as being the same number, which is weird, but that's what Einstein decided to accept, because that's what Maxwell's equations showed, and that's what the Michelson-Morley experiment showed. Okay, so he assumed this to be true. So that's the second postulate. You need to know that one. Okay, third postulate. Well, there is no third postulate. He only made these two assumptions, and all this weirdness that comes out of Einstein's theories comes from these two assumptions. First, that the laws of physics are the same for everyone, and second, that the speed of light is the same for everyone. Newton would have agreed with the first. Newton would not have agreed with the second. He said light can't behave like that because nothing else behaves like that. That's not how baseballs behave, so that can't be how light behaves. But Einstein assumed that it did. Okay, now, if the speed of light is constant, something's got to give, because there just has to be something weird going on. So he tried to figure out what it was. And so Einstein did a thought experiment, and Einstein was famous for his thought experiments. He was able to just think about this stuff and think about how things should be given certain assumptions. Okay, so he imagined himself, or he imagined somebody on a railroad car. Okay, and the railroad car is stationary. It's just parked on the tracks. And we are looking at this railroad car that is parked on the track. Okay, now we shine a light, or the person who's standing on this railroad car, this flat car, shines a light straight up, which bounces off of a mirror, and then the ray of light bounces straight back down to the ground again. So we see the light go up, hit the mirror, and come back down. Now, for this exercise, this thought experiment, we're going to assume that light moves 2 meters per second. Okay, we know it goes much faster than that, but to make the math easy, we're going to say, suppose light moves 2 meters per second. Everybody in the universe, when they see light, they say, yep, that's going 2 meters per second. So when we look at this, and if we put the mirror 2 meters off the ground, then it takes 1 second for the light to go up and hit the meter because it's going 2 meters per second, and 1 second to come back down to the ground, and the light takes 2 seconds to make its trip. Okay, 1 second up, 1 second down, 2 seconds for the whole trip. And we who are standing on the ground next to the train, we say it takes 2 seconds for the light to travel up and come back down. And a person who is standing on the train will agree with us. They look at it and say, yeah, the light goes straight up, it comes straight back down, 2 seconds. Super. But what if the train is moving? Okay, now if the train is moving, the person who is on the train doesn't see any difference. They're moving along at constant velocity, and they shine the light, and the light goes straight up, and it comes straight down, and they say it takes 2 seconds for the light. There's no difference. But we who are standing on the side of the track watching the train go by, we see that for the light to hit the mirror, the light has to be going at an angle, because as the light is moving up, the mirror is moving sideways because the train car is moving sideways. And that means that the light beam can't go straight up or it will miss the mirror. It has to be going up at this angle here to hit the mirror, bounce off the mirror, and then it has to come back down again, kind of sideways, because the train itself is moving, and their light detector, where we sent the light from originally, has also moved to the right. Okay, so that means if the train is moving, this is the bottom line here, if the train is moving, the light has to follow a longer path to get to the mirror and back down again. Now, if the train is moving at such a speed where it has to go 3 meters to hit the mirror and 3 meters to come back down again, well, we who are watching this happen, we know that light goes 2 meters per second, and it moved a total of 6 meters. So we say it took the light 3 seconds to go up to the mirror and come back down because it had farther to go. But the person on the train sees it take only 2 seconds. So when the train is moving, we see time passing more slowly. The person on the train says, nope, 2 seconds went by, and we say, nope, 3 seconds went by. Your clock, dude, who's standing on the train, your clock's running too fast. It actually took you 3 seconds for the light to go up and come back down. Okay? Now here's the weirdness. We're both correct. The person on the train is correct that the light took 2 seconds to make the trip. And we who are standing on the ground watching the train go by, we are also correct that it took 3 seconds for the light to make the trip. Because the train is moving and we are not, we are in what are called different frames of reference. And in our frame of reference, standing by the side of the track, this event took 3 seconds to happen. And for the person standing on the train, it took only 2 seconds. And we are both correct. Okay, now I want to make this very clear. It's not that the clock, the watch that the person is using on the train breaks. It still works perfectly right. It's just that time is passing more slowly for that person on the train. From our point of view, who are standing on the side of the path, we have to wait 3 seconds before their clock will tick forward 2 seconds. Time is passing more slowly for the person on the train. And that's what's got to give if the speed of light is constant. Time is flexible. Time is relative. The way we perceive and experience time depends on how fast we are moving. And time is different for everybody in the universe, depending on how fast they're moving relative to each other. This is really, really weird. Nevertheless, this has been proven. What we've done is, and we've done lots of experiments, but this is one in particular. We've taken extraordinarily precise clocks. They're cesium clocks. They watch how fast a cesium atom vibrates under certain circumstances and then counts the vibrations. If we get to a certain number of vibrations, then 1 second has gone by. So cesium clocks, nuclear clocks. And you put two clocks side by side on your lab bench, and you synchronize them so they're saying exactly the same time. Then you put one of them on an airplane and fly it around the world to the west, okay, toward the setting sun. And you put the other clock on another airplane, identical plane, and you fly it to the east toward the rising sun. And you fly them at the same speed all the way around the entire Earth to the place where you started. Okay, so one clock has gone in the direction with the rotation of the Earth, which means it's going fast because it has to go ahead of how fast the Earth is rotating underneath it. And the other plane is going slow because the Earth is kind of rotating underneath it as the plane basically stays in one place. Okay, so if you fly the airplanes in opposite directions around the world, one is going fast and the other one is going slow. The two airplanes are. And Einstein says that if that's the case, one is going fast and one is going slow, then the clocks should go out of sync. They shouldn't be synchronized anymore. Newton says that it doesn't matter. Time is an absolute thing. It passes at the same speed for everybody everywhere, no matter what they're doing, and the clock should remain synchronized. But when we do this experiment and we compare the clocks go out of synchronization. They don't match up anymore. And they drift by the amount predicted by Einstein's relativity. Okay, now you do not have to be able to do this math, but I'm here to tell you that the math is pretty simple. It's based entirely on the geometry of this triangle here. Okay, so this angle that the light has to go up to hit the mirror and come back down, that angle depends on how fast the train is moving. If the train is not moving at all, then the light goes straight up and comes straight down. If it's moving very slowly, the light has to go almost straight up and comes almost straight down. So you have a very skinny, tall triangle here. And if the train is moving very, very fast, then the light has to go at a more extreme angle. Okay, so this angle is determined by the speed of the train. And then you can just do simple, relatively simple geometry to figure out what this angle is and what the length of this side becomes. So it becomes the length of this side compared to the vertical distance. It just becomes a right triangle and use Pythagorean theorem. So it's simple geometry to figure out the amount that time changes. Okay, and I want you to remember that, right? The mathematics that you use to figure out how much time changes is based on simple geometry and the Pythagorean theorem. There's nothing exotic about the mathematics at all. It really is something anybody could do who managed to pass geometry. I'm not going to make you do it because there's not much point in it, but you could do it. All right. Now, we call this phenomenon, the fact that time goes at different rates on different moving objects, time dilation. Okay, that's the term, time dilation. So when an object is moving relative to us, time passes more slowly for them than for us. The thing that's moving past us, time is moving more slowly. Their clocks tick more slowly. And it's not because the clocks are broken, it's because they experience time differently than we do. And it's a consequence of the speed of light being constant for everybody, right? The faster the object is moving, the more extreme that effect is, the slower their clock ticks, the faster they are moving. Now, for an object moving the speed of light, time stops completely. So the closer you get to the speed of light, the more extreme the time dilation becomes. And the ultimate is the actual speed of light. Something moving the speed of light, for that object, time stops completely. That's weird. We'll talk about that another day if we have time when we can get back together. And finally, and this is important, I want you to remember this as well. We don't notice this effect in our everyday lives because everything around us moves very, very slowly compared to the speed of light. Okay, even a supersonic jet that flies at 5 times the speed of sound is moving practically not at all compared to the speed of light. So it's hundreds of meters per second versus hundreds of millions of meters per second. So we don't notice time dilation in our everyday lives because everything is moving so slowly.